We're back after a 3-day hiatus. Um, if you enjoy being outside and you live in the Pacific Northwest, I highly recommend taking a hiatus and using your hiatus to go up to Orcas Island and kayak around with your friends. That was pretty fun. Still a lovely day out today. I hear it's going to be hot. I'm wearing shorts. You can't see that, but hopefully we're all comfortable and having a good time. So, where we last left off, we're kind of doing the Julia Child, put it into the oven, take it out of the oven magic. So here we have everything that we were working on hidden behind the magic of scrolling through TMX session. And what was it doing? Let's recall. This is the kind of stuff you see if you run the scroll wheel without being scrolling. We're waiting for the survey to close. We are trying to survey this source and list its puzzle types. We were looking at Nikoli puzzles, and we found 46 types. Survey closed in 8 minutes, and we don't know what happened next. So let's all find out together. All right. So making our scroll wheel work again. Okay. And here we are. We're looking through all of the work that it did as it went through our sort of catalog ingestion formula, which is also a workflow inside of the system. So yeah, we're seeing puzzles like Akari, Hitori. These are names for puzzles that Nikoli invented a long time ago. And here we go. It's done 5 of them. The fan-out plan was for parallelism across sessions, but the first antiquarian already got parallelism within a single session by issuing parallel write calls, which is fine. I think that our primary objective for this is just to get it done as fast as possible so we don't care the means of parallelism that gets used, whether it's many parallel calls happening inside of one dedicated agent. This agent being dedicated to finding duplicates, knowing what puzzles have been made, maintaining the catalog of such puzzles. So they're kind of like a librarian for our knowledge of the pencil puzzle genre. And so apparently they were just kicking off their own subwork by themselves. Still working? All right, survey closed. 46 types were cataloged into this index. There were some thoughtful notes, which I guess we can go and read. It's drafting all of them in progress. These are standby reviewers. Be great. Could take another extra hour. Could be faster if it stays parallel. Okay, it finished in about 30 minutes instead of the 65 minutes that was estimated above. There were 45 entries staged. We already had Slitherlink, so it got skipped because we did that first as a one-off to sort of shake out the formula, but then it went and found it again. All entries schema conformant. Some class proposals were filed. Subset shading with line uniqueness. Okay, and we probably want to go look at the definitions of each of these puzzles to make sure we understand the insights that we're going to get from them. As we look at the game, we're going to be able to start defining some some of these mathematical terms. And we haven't necessarily got those under control. This is certainly like a learning area for me. We've got 3 other entries held in staging. This is interesting that anything should be duplicated across the existing Nikori ones. 6 class fit caveats were flagged in the merge notes. Some open questions. I'm not sure where those are. Read the merge notes, decide the 3 class proposals, then I will sling to one of the standby antiquarians. Okay. Yeah. Okay. So, I don't know exactly what this means yet, but let's keep our hands on let's go read this, the merge notes, and see what we get. Catalog staging runs, Nikoli merge notes. Here we are. We in the right? Yeah, we are. We're on the right file. So now that we've had that run, it looks like we'll have an updated file longer than 21 lines, I assume. Oh, no, maybe not. Okay. Hmm. Interesting. There's a uppercase, lowercase thing going on here. Here's the index file. That could get confusing. All right, the full sweep of Nikoli's puzzle index. Nothing new for Slitherlink. We've got a whole bunch of new puzzles. Warning indicates entries where the seed class assignment is a stretch. The structural fit is loose. So those would be, let's see, going back through here, we've got Erugofu, I assume, Gorufu. We've got Nansuke, Nurimezu, pencils, Ensuru, Impitsu, I don't know. Usawan, class fit caveats. 3 formal class proposal beads were filed. Hitori, subset shading with line uniqueness. It's not captured by any existing seed class. Per region counts, not per row or column uniqueness on a subset. We'll figure out what this means when we look at Hitori. Ashiwo Kakero. Again, it's sort of like hard to visualize the rules from this classification. Number link. Okay, we do know what number link is. Number link is where you start with 2 different endpoints, and then you're supposed to draw the path between them. And you're supposed to cover all of the grid, and none of the paths can cross. The canonical k-vertex disjoint paths problem on a grid. The existing seed class chain with cell numbering describes sequential numbering, which would mislead readers looking for collisions with disjoint path puzzles. There's literature on k-disjoint paths, and so this is what we should call it. Yeah, I think this is exactly the kind of insight that we're looking for, and why we're assuming that we're going to have to grow our schema, both because we've got puzzles that are similar to each other but distinct, and also because there's actually some literature about it. All right. A multi-graph realization with per vertex degree clues. That would be how many edges are coming in and out through this node. Planarities, non-crossing edges, and global connectivity. Oh, bridges? Is that what this is? The closest fit treats bridges as objects. So if so, then I do know what this is. It's a series of islands, and hopefully we'll get to it through the documentation a little bit. We have got, I've got a program called Krita going. It's a sort of simpler painting program that it's kept all of our annotations from previous, but now we are sort of just opening the pages as PNGs, like so. And we're getting each of the new puzzle types onto a new PNG. So we were doing this in order to just go through the World Puzzle Grand Prix for fun. But we might also be able to learn about new puzzles this way. And just have something to do while we're waiting for the mayor to get done. Slow the link very well. I haven't seen this one before. That's cool. It's sort of like a Picross, but includes adding. Let's see. What page was that? Page 6, page 7. Yeah, these are just the ones I think for this particular Grand Prix that they wanted people to get ready for. But if I go look, I'll look for a reference really fast for, I would call it lantern. Well, bridges. We're doing bridges, right? Hashi wo kakedo. And then we'll all look at it together. Yeah, okay. This is what I thought. So check out Hashi wo kakedo with me. There we go. Build bridges. It's been published under the name Bridges. It's been called Chopsticks because there's Hashi in it, but Hashi, sort of a homophone. You could say homonym. I would say homophone. Homophone in Japanese. There's a different Hashi that also that means chopsticks instead of bridge. All right, so let's look at this puzzle on the left here. So the puzzle is the given information of just these numbers in this grid, and you can kind of see that the numbers are vertically and horizontally in the same row and column as some of the other numbers. And the rule of Hashi wo kakedo is that on each of the islands, we have the number of bridges that are coming out from the island to other islands. We can have up to 2 bridges in one direction, and they're either vertical or horizontal. And so you can see that for this 8, we actually know where all of the bridges are going to go. It's sort of maximally filled, and it's 2 bridges in every direction. Fact. Let's just save this image. Here, we can like work out this Hashi wo kakedo puzzle really fast. Set of Koda. Okay, so here's our starting point. Get out our brush. I think it's good. We've got a color selector over here. We can make our bridges brown, but who cares? All right, and let's start going. So here we've got 2 bridges, 2 bridges, 2 bridges. Sorry for my drawing. 2 bridges. The other rule in Hashi wo kakedo is that bridges can't cross. And so drawing a bridge from this 3 to this 1 now would be illegal, right? The bridges don't there are no over and underpasses. So you can kind of see how we consumed all the bridges that are destined for this 2 here. So there's no way to draw another bridge to this 2 without violating that vertex count if you want. Another rule is that all of the islands need to be connected together. That forbids us from drawing a bridge from this 1 to this 1, because then they would both be satisfied and it'd be like a bridge network that wasn't connected to any of the rest of the puzzle. So that would be illegal. Seeing that there's no way to draw from this 1 to this 2, no way to draw from this 1 to this 1, this bridge has to go here. I don't know why it's so hard for me to draw with a mouse, but there you go. And then this one is also, we're sort of highlighting that it's been completed, if you want. Similarly, this 2 has only one place to go, and it's done. This 1 is sort of boxed in. It can't go to this island or through these bridges. It has to come up this way, and it's done. And this 3 has also been consumed. And notice as we finish parts of the puzzle, it's sort of like we are cutting that part of the puzzle off from the rest of the puzzle. So you could imagine that this puzzle, as we've drawn it so far, is equivalent to another puzzle where the satisfied nodes have been removed. So, and then the corresponding numbers on their bridges have been decreased. So if we cut off the puzzle right here, we might make an equivalent puzzle by changing this number to a 3 to account for this one bridge that had been done, and then just continue to work the rest of the puzzle. And similarly for this 8, you know. So you can think of this as sort of having divided the puzzle into smaller and smaller puzzles. One thing to note about 3s in a corner like this is that there's no way to sort of avoid putting a bridge in both directions coming out from it. To see that, we sort of fill in all of the bridges that we can in every other direction, like 2 bridges from this corner to this 3 island over here. And there has to be one left over, at least one over here. And by similar logic, if we filled in 2 here, maxing out this direction, we'd still have to throw 1 over here. And the same kind of thing is happening for this one and this one. Notice that we've cut off this 3 now. It's satisfied all of its requirements, 1, 2 from the 8, and 1 from this 3. So we can kind of cut it off from the puzzle. We're left with this 2 sort of all by its lonesome that needs to have somewhere else to go. So its second bridge would be right there. Now it's been satisfied. This has been satisfied. And there we go. Okay, so that corner of the puzzle is kind of done. This one has nowhere else to go but over here, and it's satisfied. 2 is satisfied. We have a 3 in the corner kind of situation, so we need to draw both of those. This is satisfied. The 4th one is going to come over here. This 3 only has one place to go. There we go. And so all of this sort of edge of the puzzle has been satisfied. And you, kind of keep going in this manner. Sometimes there's slightly more interesting inferences to do, like especially when you have options about which way to go on each one. For this one, we have no more options. We've done our max of 1 into this sort of cutoff portion of the puzzle. We've got 2 down to the 8, and then this one has to come over here. 4 is satisfied. This 2 has nowhere else to go. And this 2 has been cut off from the rest of the directions by that bridge. I mean, it was like this from the beginning anyway. It's done. Yep, all of these portions of the puzzle are connected together so far. So our final job is to just make sure that all of these nodes stay in the network. It's kind of hard to imagine not doing that. We can do at most 1 bridge in this direction from this 2 to this 3. So we need to have somewhere else for the other bridge to go. It has to go that way. We've got, it's possible that another bridge could go this way from the 5 to the 2, and that would satisfy the 5, or that it could go up this way, satisfying this 3. So we're kind of picking between these 2 worlds if you want. It looks sort of like it could go either way, doesn't it? This is one of those weird, here, I'll try and show you those 2 worlds, right? So here we have blue satisfying this 3, and then we have, and also this 5 at the same time. And we're satisfying this 2 and this 3. So that's one way to do it. And then the other possible world is instead of going this way, we come over this way. Then use these ones. I think that these solutions are equivalent in that they both satisfy the network, and then all the node degrees are satisfied. Yeah, I'm pretty sure that's true. I might have to, check my work a little bit on this kind of thing, but as one does. But I think so. I think either set would work. So that would violate sort of the usual rule that that there's only one solution. Well, if you look at their solution for this, um, the difference is right over here. They chose the blue lines, basically. Look at that again carefully. So, yep, going from the 3 to the 5 and the 3 to the 2. Um, let's see if we can see again if there's some problem with going both to this 5. It says one of its solutions. Okay, so the other one is the other one we found. This one says that there's a moderately difficult one. You can see that there are more nodes. It's not necessarily that both sets of nodes be on exactly the same grid, right? Some of these are sort of diagonal from each other, or they're going in and out of odd and even or something like that. All right, anyhow. First appeared in 1990, though there was an earlier form that appeared in 1989. Cool puzzle. All right, let's go back and read the that with this sort of knowledge of how that puzzle works. A multi-graph realization. Per vertex degree clues, so that's the number on each island. Planarity, which has to do with the bridges not being able to cross each other. And global connectivity, meaning that everything has to form one gigantic island network, if you want. The closest fit, place objects with row column counts. I wouldn't say that that's true at all. There are no row column counts. Like, nothing says that there should be so many bridges in like this column or so many bridges in this row. Yeah, so there's no such row column count. Yeah. So yeah, I would definitely buy that one for this. And I think that we kind of understand what it's telling us as well. Why does it say this is a multi-graph realization? Maybe it's because what we're starting with are all of these little pieces that we're putting together into one big piece. But maybe multi-graph is like a different jargon term that I'm not familiar with. You can see how far I went in the algorithms and graph theory. Not that far. Solving is a matter of procedural force, it says in the Wikipedia. Yeah, you're reading this with me. Having determined where a bridge must be placed, it could eliminate other possible places for bridges, and so on. Yep, absolutely. Common practice to cross off or fill in islands. We drew the little squares around them, kind of the same. Yeah. We talked about two islands that were one next to each other. Yeah, any bridge that would completely isolate a group of islands from another group would not be permitted. I mean, this is a kind of a similar insight to this one. Determining whether it has a solution is NP complete. Yeah. Okay. Cool. So I think we understand that one very well. Yep. Number link. Hidato style sequential numbering. Let's look up Hidato. Yeah. Oh, okay. I haven't seen this before, but at least I don't remember doing one of these puzzles. It's interesting though. Sorry. Here we go. Okay, let's look at Hidato for a minute. Hidato. We were given some numbers in the grid, and we need to go from the beginning to the end, 1 to 40, putting in every single number, and we are trying to fill in the grid entirely and make it so you can step from one number to the next, either vertically, horizontally, or diagonally. So, shall we do this puzzle? Why not? If there's no joy in your work, then you gotta make some. I don't know if it's doing SVG. Is it? Did I download it correctly? It says it would do SVG. Oh, download the original. It says it's by Life of Riley, who we can credit now. I guess Life of Riley on the Wikipedia or in the Wikimedia Commons. So thank you for this puzzle. All right, here's our Hidato puzzle. Okay, cool. So let's get started. Like inferences that we can make. 33 and 35 are next to each other. So whatever thing we choose for 34, they're going to share that cell. The only cell that they share in their neighborhood is this one. So this is where 30. Oops. Oh, sorry, we gotta totally forgot this. Let's add a paint layer. All right, now we should be good to paint. And now we're gonna see my atrocious drawing of numbers and letters. I guess I could use text for this, but you know, whatever. We need to get from 33 to 32. And if we stuck it right here, we'd have to put 31 in this cell. And then there'd be no way to get from 31 to the rest of the puzzle. So it can't be stuck here. It's got to be stuck right here. 31 has only one place to go. Okay. We've got a couple of different options for 23. It could go here or here. Maybe we should just draw those in. As I said, I've never tried to solve this exact puzzle before. We've got 24 and 26. These have to reach each other either this way or this way. Obviously, one of these solutions doesn't work if we put the 23 here. And we can't put 25 here as well. 11 and 13 need to share 12. That's right here. Choice. 9 and 11 need to share 10. Yeah, this is the only one that they both share. 7 and 9 need to share 8. Got to be right here. Okay, and now we actually know where 2 is. We've eliminated most of the ways to get to 2. We've got 5 down here, so we've got to get 3, 4, and 6 out of these 3. 5 and 7, we're going to share that 6. It's going to go here. 3, 4. We've got 7, 8, 9, 10, 11, 12, 13. That's interesting. Okay. And it's sort of like, how are we going to fill in this number? One of the neighbors of this number has to be exactly 1 away from it. I would venture it's going to be 39, but I don't think we have like an inference that says it has to be. We need to get into this corner from 13 to 18 and then get out again so that we can return to 2021. Here's an interesting observation, perhaps. If we went this way from 18 to 19, then 20 would have to be over here, but it's not anywhere next to 21. So it's not possible that that would be our line for 18 to 19. We could do 18 to 19 down here, but the problem's even worse. We could get 20 here, and then we can't get to 21. So we have to pick the last option, 19. And then from 19 to 21, they've got to find one number to share 20. That's the only choice, the only option available. Did I stutter? Yeah, yes I did. Let's see. Recall again, we've got to get, so this is sort of how 18 is getting out of this corner, but we've got to get 14, 15, 16, and 17 into this corner. I think this is the only way to do it. 14, if we chose 15, then we couldn't possibly get 16 and 17 before 18. So 15, 16, 17, 18, 19, 20, 21, 22. So if we put 22, 23 up here, interesting thing happens. We've got no path to get from 35 into this side to get to 40. So we've got to put 23 right here. It's funny, I don't know if we have eraser in this drawing program. We've got, yeah, that's not it. Okay, as we mentioned, we've had two options for 24 to 26. Here's the other. And from here, 35 only has one place for it to go. 36. We're sort of on rails to get 37, 38, 39. If we tried to skip past that, we would create a hole in our grid. There we go. So we know how this puzzle is going to end. There. All right, we just have to fill in the remaining numbers. We've done everything from 1 up to 22, 23, 24, 25, 27. We're going to get 28, 29, 30. And again, there's just a very on-rails way to do that. So that is Hidato. Yeah, Hidato. Okay, and that was an easy one. You can kind of see how there could be more complicated inferences that we'd have to make based on finishing the puzzle, ensuring there are no holes, taking possible alternatives. And if less of this information was given, maybe the puzzle would be unsolvable, but also it would be just more complex to reason through. All right, so let's return over here. Chain with cell numbering describes Hidato style sequential numbering. So yeah, it's not really like the number link puzzle where you draw paths between ends of the same color. Disjoint paths with given terminals. I think that's a fine way to describe it. And then last, let's look at Hitori. Okay. Yeah, I was recently playing Hitori. They call this a different thing in Simon Tatham's portable puzzle collection. But the basic idea of Hitori is that we start with a grid that has a number of numbers in it, and we have a restriction that in any single grid, there is no, oops, sorry, kind of hard to scroll the amount I want. We're hiding this solution here. And again, let's do a Hitori. And then this is my own work, Dan 1980. Thank you for your puzzle, Dan 1980. A Hitori. And Hitori means like alone or one person, as it says in the Wikipedia page. And the reason that we're trying to get them alone is that so that in their row and column, there's only one of this number. So we can't have two copies, like two fives. And as well, there's a restriction that the way that we get rid of numbers is by blacking out their cell. So you could imagine like if we decided that this 5 was not going to be the correct duplicate, we would fill it in. And then we have a rule that there can be no two black cells next to each other. So filling this in, saying that there's no number there, is going to imply that this 6, this 4, and this 5 are all going to be used. So one of the sort of early seeds that you can use in this kind of puzzle, certainly if a number is already unique in its row and column, then we can just accept it. It won't have any, oh, whoops. I'm not brushing again. There we go. this 7 I think I was looking at. So there are various ways to do this. In Simon Tatham's, we circle things that we're going to keep, and we mush over with squares things that we're not going to keep. Another thing that we can use for inferences has to do with finding two of the same number across from each other, or with like one skip in between them. Let's look for that situation. So it's sort of like we're looking for a number, a second number, and then the first number again. 3 in a row, horizontally or vertically. I'm not seeing a lot of that. Here's one. 8, 2, 8. So think about what would happen if we got rid of this 2 right here. So we'd blank it out. Then we'd follow the rule that we have to accept all the numbers on all 4 of its sides. That would be part of the solution. But that would cause there to be 2 8s in this row, which is forbidden. That means that instead of crossing out this 2, we have to keep this 2. Now look what happens down in this column. We've kept a 2, but we've got another 2 in the column. That means this one can't be real. Consequently, all of the ones next to it are going to be kept because we can't have 2 blacked out cells next to each other. So we're keeping a 4 and this 3 and this 5. There's another rule I haven't explained yet, which has to do with making sure that all of the accepted cells, all the ones I'm circling, they have to be joined together in one big glob. And so we can't use our cells, our black cells, in such a way that any of these white cells will be cut off from the rest of the puzzle. And sometimes we'll make an inference using that as a clue. All right, let's look for some more things that we might know. When we circled these new ones, we were sort of scanning their row and column for any duplicates because those could be crossed out, and that would provide fodder for us to continue, finding more numbers that we're forced to accept and continue solving the puzzle. Sometimes those kinds of things can chain together. For instance, like if I X out this 5, then I have to accept both of these 1s. That would X out this 1, and I have to accept both of these. And eventually, like through this chain of consequences, we could go, oh, okay, we've derived a contradiction. That thing that you crossed out at first, it can't be correct. You have to accept that number instead of crossing it out. So let's see if we can find some more. We know that one of these numbers can't be used. So one of them is going to be accepted as the 8, and the other one is going to be blacked out, which is going to bring in either this 2 or this 5, or this 6 or 7. And it would also sort of promote this 4 or this 6. This 4 doesn't have any contradictions in its row or column. It can be accepted. The reason that we might do this is because, number 1, we'll know it has no bearing on the puzzle. And number 2, it might show us that there's an area of connectivity because we're supposed to connect all of the white squares together. For similar reasons, this 7's got to be accepted. It has no rivals in its row column. This 3 not necessarily, this 8 necessarily accepted. And these are sort of vacuous like observations. They're not helping us place all of the dark squares on the puzzle. That essentially is like how we know we've finished the puzzle. Right, because they're not eliminating any contradictions in the setup. Here's one I didn't spot before. Since this 2 was accepted, this 2 is illegal. So there was another, besides this contradiction we found of 2 2's in this column, we should have also done this 2 2's in this row. All right, and now we're going to start seeing some chain reactions because accepting this 3, we'll look down the puzzle and we'll see, oh, there's another 3 here. It can't be used. And you can kind of see how it not being used means that we've got still more places that we know we're going to use. And the way that I like to do this when solving is, circle them one at a time, look for any downstream consequences. We're looking for 5s in the column or row. We're looking for 6s. And then if we conclude with those sort of no more consequences, and we'll still back off and we'll look for another blacked out cell that hasn't had all of its numbers circled yet. Now we're looking for more consequences and more consequences. Turns out there is a consequence for this one because in its column there's a 4. Yeah, blacked out. Before we do the 8, notice what happened to this 3 here. It's surrounded on 2 sides by blacked out cells. If we black out the 6th cell, this 3 will be cut off from all the other circled cells. So it actually has to be accepted, not blacked out. And that will cause this 6 to be blacked out or not used. And we also have this 8 from this 4. We're just going to keep returning to that as long as we have some more of those to look at. We see there's no 8 in either row or column from the beginning of the puzzle. Let's just, sometimes doing these puzzles feels a little bit like cleaning. It's like there's no thought to me like circling these numbers. It's just immediately demanded by the rules. Not making any inferences, just doing what the rules say. And we've got some more to say about that. It's easy to visually scan the grid and look for blacked out squares that don't have circles next to them. It's not easy to visually scan the grid and say, oh, well, this 2 is about to get blocked in by these 2 cells. Let's circle the one next to it. Yeah, and you can always easily return to searching for neighbors of blacked out cells, but you can't always easily return to spotting inferences like, okay, so if this were blacked out, this 4, then that would block in this 7 away from the rest. So it has to be used. When I circle something, I'm always looking for clashes, coloring those in. So this is how we do Hitori. Let's just finish it real fast if we can. Let me know if you have any questions about this puzzle type. Remember, we're not just puzzling for puzzling's sake, although it is fun. We're trying to unlock intuitions about what kind of puzzle this is. When we use all this mathematical jargon, what's it really trying to say to us? All right. 8. Maybe this is a slow way to learn that. Should I be reading a paper right now? Or should I be drilling these concepts into my bones and having fun? I think you know what the answer is. And this would be slightly easier on a touch screen. Absolutely recommend Simon Tatham's Portable Puzzle Collection. Has an implementation of this one. All right, we've still got a few clashes to go through. We haven't found them all. At the end, after we've done all of these inferences, we should be able to make a judgment on every single cell. There shouldn't be any sort of loose ends where it's possible that it could be a closed or it could be open. It could be blacked out or it could be used. Every single cell is going to have a determination. All right, I think that we've come to the end of all of the blacked out cells. Oh, wait, here's another. Blacked out cells with neighbors. Oh, and just as I speak, of course, we get a new blacked out cell. All right, a 1. I don't see that in either row or column. A 3, I don't see in either row or column. We can spot things like this. You can see how we're trying to cut off this little portion here, 7451. If we blacked out this 6th cell, that would do it. So we can't do that. We have to accept that 6th cell. All right. There's no 6 in row and column, so this is vacuously true. There's no 5 in this row and column. So vacuously true. Here's an interesting one. We don't want to cut off this 2, and we have these 2 black cells, so we'll accept this one, and we'll black out this one. Now, notice that we didn't learn anything new from this because all of its neighbors are already accepted. Let's see, what else have we got? The 6 is going to be vacuously used. No rivals. Oh, this 5, we missed it earlier. This 5 actually had 2 rivals. This one down up here, this one down here. And that's important because we got a 7 out of that. Not that that 7 went anywhere. It was vacuously, it never had any rivals. This 4 here would block in this 3 away from all of its friends, so we can't have that. This 3 and 4 are threatening to cut off these 6, 7, 8 away from the rest of the puzzle, so we have to keep this 1 and that. So we have to cross out the 1 that is its rival. Maybe I would have called this puzzle Rivals. I just noticed there's a 6-3-6 formation here. So from the beginning, we could intuit that blacking out this 3, it would have caused a 6 and a 6 in the same row, and that wouldn't work. Yeah, we're coming close to the end of the puzzle. I'm looking for other inferences to make to finish it off. This 3, vacuously available, no rivals. We've got this 6 and this 6, this 7 and this 7, and that's just about it. I guess the interesting thing about this is that if we blocked out both this 7 and this 6, then that would block in number 5 into a little corner, into a single tiny cell in the center. We can't have that. Here it is. So here we've got 3 sides of this 5 filled in. We can't fill in the 4th side, isolating it from the rest. That'd be this 6. And now we're using that fact I just mentioned. We can't fill in the 4th side of this 5. I do this one. And that is our answer. So we've got black spots on 1, 3, 7, numbering from cells. As this is column number 1. 1, 3, 7, 6, 1, 4. And then we can check that back against the solution that's given in Wikipedia. Right down here. 1, 3, 7, 6, 1, 4. Yeah, it's the same. We can sort of flip back and forth for a minute, and yeah, we'll see that we did it right. 1, 5, 8, 2, 5, 5, 7. This is how 1, 5, 8, 2, 5, 7. This is how the World Puzzle Grand Prix actually does its puzzling. It shows that you do checksums on rows instead of trying to like rewrite the whole answer so that someone can check your whole answer. Sort of long and boring. This is interesting. My stream manager says I'm offline, but it's probably just out of date. Yeah, okay, we're live. No problem. We're right here. That's what I thought. Just checking. Okay, so let's return to this. Hitori. Subset shading with row and column uniqueness on the unshaded complement. Yeah, so we're shading some of the grid. That makes sense now. There's row and column uniqueness. That has to do with 1 and 1. Can't be in the same row. No rivals. Non-adjacent shading. And connectivity on unshaded. That's making sure that none of the unrivaled numbers remaining are separated from the rest of the group. Region fill with region cardinality. prescribes per region counts. So it's referring to like Norikabe, I think. Okay. All right, let's return to our mayor. Oh, and I'm obviously trying to type here, but it's still scrolling. Let's see. I read the 3 new class proposals. I agree that they capture the new formalisms discovered, and the old ones don't really fit. We should use them. Now I'm actually kind of curious about the other 46 ones. We started with a certain small subset of class proposals, and I'm sort of surprised that we got coverage on 40 other puzzles from them. That's pretty cool. What's cool about it is it means that our framework is flexible enough to accommodate them, and that our enumerations are kind of well chosen because they're spreading themselves out across all of these different tasks, all these different labeling tasks, if you want. Okay. Let's see, what else did we get here? So that's the 3 options for the review gate. I do think it's good to sort of keep your hand on the wheel there. The class fit caveats are in merge notes. Let's go back and read that some more. So we went through all of these vocabulary additions, and I think that we kind of convinced ourselves. Right. Okay. Chain with cell numbering. It's a best fit but loose. Edu Golf. Chain of decreasing length straight strokes from ball to hole. I've seen this one before. It sort of says that you start with, you start from a ball number, and you're trying to get it to an associated hole, and you need to, well, maybe not associated, maybe that's free. There are a bunch of holes on the grid, and there are a bunch of golf balls, and the golf balls have a number, and the number dictates how many strokes you need to get from ball to hole, as well as saying that each stroke that you take, a vertical or horizontal move, is going to be decreasing in length. So 5, 4, 3, 2, 1. And we also have the planarity, don't have golf strokes crossing each other thing. The geometric stroke length is decreasing on each move. There is a way to interpret Heru golf as cell numbering, which is that we're going to, starting from this sort of golf ball, we're going to number the cells 5, 5, 5, 5, 5, 5 times, 4, 4, 4, 4, 3, 3, 3, 2, 2, 1, 1, 2, 2, 1. Yeah. So that's interesting. All right. Non-skay. A crossword placement puzzle with digit alphabet. I'm not sure I understand what it's saying. So once again, let's go learn about non-skay. Oh. This isn't in the Wikipedia. That's interesting. Oops, come on now. It started suggesting, okay, number skeleton. Fill in the blank cells with the numbers in the list. Numbers are up, down, or left to right. One cell has only one number digit. Oh, okay. I'm actually familiar with this, I think, in a completely different context. So, in the Dell puzzle books, there is a puzzle called Crisscross. That's what this is. We're given a sort of word list, and we're given sort of the incidence of each of these words. The word list, they're all unique, you can kind of see. And we're given a crossword where all these words have to be used. And for every single word in the word list, there is a space in the grid somewhere. You can kind of see there's these two cells here. There's a two cells here, two cells here, and two cells here. And also they made the grid symmetrical. Not necessarily do, but it's done for like crosswords sometimes. And so into those four cells I named, we're going to have to put these four numbers. And those numbers are parts of other clues. So we're going to have to make sure that we can get the entire grid together. And you can see there they put a solution. Well, let's just do it again. We're going to put the entire grid together. And basically we should use each clue once. And we shouldn't see any like contradictions or anything like that. Okay, well this is nice. It just gave us the puzzle. I didn't like memorize the solution or anything like that. We've got two options for this 4. We've got 1, 3, 5, 3. Notice how putting 1, 3, 5, 3 here would require us to have 3 be the middle number of one of these clues. Not possible, so we have to pick the other one. Okay, and when we use it, we can check it off. By process of elimination, we've got to put 1, 3, 5, 3 down here. This one has to start with 3 and end with 5. There's only one of those. This 2 has to start with 3. Only one of those. You can see that they're kind of alphabetized, and that's something that would happen in the. And notice that due to this ambiguity, there's nothing constraining us to help us tell whether we should put the 1 or the 3 here. We have to wait for the rest of the puzzle so that we can eliminate those possibilities. We only have one 2-digit number that ends in a 5. We only have one remaining that ends in a 1. All right, so by process of elimination, this one has to be a 3. We're looking for a 3-digit number with a middle of 5, and there's only one of those. And then we've got our last clue. There we go. So that's non-scale. Number skeleton. Okay, let's go back and see what it was telling us about number skeleton. A crossword placement puzzle. Exact cover on row column region incidence. Crossword placement. There is something interesting about having a set of words that have to be placed into the grid. I can see why it wants us to talk about that. I don't know what the other puzzle is that is being called exact cover. In other words, like there's some other puzzle in our list that Nonsuke is getting lumped into, and we might want to look at that and see what the similarity is. Let's see if we can find it. We have this catalog of entries. Oh, I guess Slitherlink is the only thing that made it in there. Huh, that's funny. Ah, there we go. Okay. It's just in the staging. So somewhere in here, let's ask the mayor about that. Mm-hmm. Maybe we could use some tools to index into the catalog or look up entries by attributes. I don't want it to like reinvent SQL here and stuff. I was looking for we're reading the merge notes. Exact cover. To compare your non-CK. How similar they are. And I had to grep for it. Exact cover on row column. Now let's do the thing that we pulled it. We already did. Where are we exactly? We're in the catalog, staging. Okay. That thing that we were talking about in catalog staging. Okay. So there are actually 5 puzzles or so. Okay. So Sudoku, we're all familiar with, but it's about filling in with no row column contradictions, a grid. Kakudo, also no row and column rivals, you could say. But each row and column has to sum to a certain number. Makaro, I'm not sure I recognize. Given a rectangular grid pre-partitioned into rooms, regions, fill every white cell with a positive integer such that each room of size n contains the integers 1 to n exactly once. Oh, okay. Right. No 2 orthogonally adjacent cells of the same number. For every black cell with an arrow, the arrow points to the cell containing the largest number of the neighbors. That's interesting. I've never seen this one. Let's look at it. Well, at the very least, if all of this comes to nothing, if it's no longer important, then at least we'll have had fun learning some interesting puzzles. Here we go. So it's like I said, in a region of size n, then it should point to we're going to fill with the numbers of 1 to n. So this 4 region is going to have 1, 2, 3, and 4. This 2 region is going to have 1 or 2. 1 or 2, 3. We're not, no adjacent numbers. Each room contains all the numbers, yeah. In the black cells with arrows, the biggest number among the up to 4 cells around the cell with the arrow is in the cell the arrow points at. So that means that whatever this is, it's got to be bigger than these next ones. I think the only way to do that is making it 2, because it can't be bigger if it's only 1. If it were 1, then it would be as big, but not bigger. Forces us here. And then a number can't be next to the same number in another room. So that would imply we've got to do this, and this. 2 can't be next to a 2, it's got to be 3, 2. If this were a 2, then it couldn't be a 3 over here. It would have to be a 1. If this were a 3, then we can't tell. This one can't be a 1, and this one can't be a 1, because 1s can't be the biggest. That leaves this right here. This one can be a 2 or 3, but the 2 can't be next to a 2, so it has to be a 3. This one is a 2. It would be ambiguous which way to point the arrow if there was another 2. I think that's how this rule is used. It would have pointed to this 3 if it were the biggest, but it's not, so it has to be even bigger. This is next to a 1 and a 2, and they can't be the same. This is next to a 2, and they can't be the same. This is next to a 4, and they can't be the same. So that would be my solution. Yeah. Yep, looking at the Nikoli solution, that's it. All right, so that's Makado. It does have some similarities with some other puzzles I've played in the past, which I'd say that it's most similar to a puzzle called Unequal, which is kind of a Sudoku-like, in that you're filling in a grid and you can't have the same vertical and horizontal, and no rivals again. And there are maybe less than signs or greater than signs between different cells, and they have to be strictly greater than or strictly less than. And using that and some starting clues, you can figure out how to fill in the whole puzzle. So there's some like similarity with Sudoku there. There's another one very similar. These are in Simon Tatham's, by the way. That has to do with equal, unequal. And I might be forgetting that. Exactly what you're supposed to do with that one. It has to do with adjacency. So the unequal one has these greater and less than symbols. The adjacency one says that you can't have 2 numbers with adjacent values. Well, let me see if I can summarize that well. Okay, there's some lines in between each cell. Lines in between 2 cells indicate that the 2 numbers are adjacent to each other. So either 1 up or 1 down from each other, like 2 and 3 or 4 and 5. And then if there isn't a number, a sort of line in between those cells, then they have to not satisfy that property. They can't be adjacent to each other. So, for instance, if you see a 4 and no line next to it, then the cell next to it can't be 3 and it can't be 5, because those would be adjacent, and we know because the line is missing, they're not adjacent. So all of these puzzles kind of fit into a certain mental category for me. So yeah. A partial order propagation layer. Yeah, I would agree with this. All right, we were reading merge notes to understand how this is conceptually loose. It doesn't quite capture the idea that there's a global list um, has some similarities to other but I think the possibility that the same value can be used twice in the same in a row and column, and the presence of a global list to cover by filling in the grid differentiates it somewhat from the other exact cover puzzles. All right. Um, let's add about the judgment on Herigal. That's fine. I didn't show you all that one, but you can kind of take my word for it. Fine. I would recommend splitting it. Trying to think if there's any other way to put how the clues provide constraints on each other. You know, that the first letter of one is the third letter of the other one. All right, let's keep going. Nuri Meizu. I don't know what that is. I guess maybe it's just fastest to. Oh, yeah, I've never heard of this before. Let's look at it. Make walls by painting cells. Create a maze which goes from start to goal, I guess, across only white cells. The areas enclosed by bold lines are called rooms. All cells in a room have to be painted over or left white. White cells cannot be entirely cut off by painted cells, and white cells must not form a loop, because that would we could get lost in the maze trying to go through that loop. We're trying to make one direct route from start to goal. Start, goal, circle, and triangle can't be painted. The circle cells are on the short way, the shortest path from S to G. And there are no cells with triangle on the shortest route from S to G. Black and white cells cannot cover 2x2 or larger squares. So we can neither have 2x2 white or 2x2 black. Okay. Cool. I don't know how they got to this. Let's do a Nodi Mesu. Okay. It feels like we're sort of struggling uphill a little bit. you know, we're on, how do I say this? We're just on a path of learning. I see. All cells have to be painted over or left white. So it doesn't mean that each cell has to be painted over or left white. It's all or nothing. Use or don't use. The other thing I'll note about this puzzle is that we're kind of looking at this graph like this. We're deciding which edges we want to use to go through this maze. We know that there's not going to be the path through the triangle, so I'll just sort of omit those. They're sort of like, we don't want to go there. So you can see that there is like a dead end here. We're not going to want to go this way. But also, there is like no way to cover up this white square in the room. It has to be still there. By a similar token, we can't color in this S, so we can't color in its neighbor right here. It's got to be part of the puzzle as well. I don't know if that means that we have to go through it, but there might be a certain rule about it would imply that if we have to keep these two, then we can't have this one, and that's because it would violate the 2x2 rule. Can't have a 2x2 white, so we'll darken all of this. So already we're kind of getting somewhere. We know that our path from the start has to go through the circle, and it sure does. And it can't go through this triangle, so we know that we'll get to here. We know that we got to here, so we can't darken any of this. We can sort of see that there's no point in going this way. And so I don't know why it's necessary to darken, except that we'll have, we know that we're keeping these, so we would violate the 2x2 rule, I guess. So already we have a pretty large amount of information about what's the path to our goal. And now we have this final goal, which is we won't necessarily go up this way, but we got to at least here. Here, I'll just sort of like, this is our route through the maze, right? We're definitely going to go this way to stay on our circles and avoid our triangles. Now, should we turn right or should we go straight? What is the puzzle telling us? Well, right now we've got 2 white here, and we've got a white here for the triangle. If we left this white, then that would be a 2x2 area that is all white, so we can't use it. So we've got to go this way and then this way. I guess that's it. That's the puzzle. All right. We didn't use the thing about not making a loop. You could imagine that like if this was split into another room, maybe we would have to eliminate this to prevent this loop from going. Because we're sort of trying to idiot-proof the traversal of the maze, right? Like, there's only one way to go. Don't go through any of these doors. You have to go through these doors, and you'll arrive at your destination. Okay, might be fun. I don't know how complicated these can get. Now that we know what Nodi Mezu is, region fill with region cardinality. The structural innovations of white cell tree topology, shortest path and circle, are not covered by the seed class. Re-examine if more shortest path clues are fine. I think that's fine. Yeah. The judgment on Mesu seems fine. Suggests that maze creation and the graph not looping constraint seems to have to do with making a tree out of a graph. All right, let's keep looking. Pencils. It's been a while. I think I've seen this one before. Let's look at pencils. You have to mark out pencils, draw lines from the tip of the pencils, and use the number in the pencils. Okay. Let's try. Okay. So we know that each number is going to be on a different pencil. Looking at this solution a little bit, it doesn't seem like it matters where the number is in the pencil. So we know that a 4 is springing out from this corner. 1, 2, 3, 4. It's going to have 4 cells in it. And there's really no option about where to put those cells. And then at the end of that, we're going to draw the pencil, which is a triangle with a tip to the center. Okay. Similarly, here's our 1, and we're going to draw a triangle to the tip of the center. And after the end of the pencil, we're going to draw a line, a path that is this number of cells long. So 1 could go either down to this one or across to this one. The tip of the pencil is indicating that the barrel of this pencil has to go behind it, like so. This pencil has to go backwards at least 1. We don't know if it's a 1 or a 2. And are we going to fill the line from a pencil? Can't cross itself or branch off. The cell shows the length of the pencil. One pencil may have no one or several numbers in its cells. Yeah. The line goes through one or as many cells as the number in the pencil. At least one, though. Okay. So, okay, so they do an inference like this. So we've gotten as far as we can go. We're not sure which way this 2 pencil goes. We know that this line starts at 2, but we don't know which way it goes either. And we've got this line starting, and it's got to go 4. It actually only has one choice. 1. Can't go to the right into the other pencils. It's got to go 2. We actually don't have any option for where this pencil goes to. You just stick that in there. It's got to go at least 1, right? 1, 2. Now there's no other way to go. 3. And finally, 4. Now, to get a pencil of size 2 here, the barrel is going to have to go like this. And that sort of X marks the spot. It's done. Here's a 2. There's nowhere other place for this 1 pencil to go to than right here. This is going to go 1, and then it has no other place to go. It'll go 2. This has to go 2. It'll go 1, 2. There's really no other size for this to be than 1, so we know that it's done drawing. And that's it. We've filled in our puzzle. Cool. So that's pencils. Polyomino packing with given counts. The convention of the length number pencil only, line only, or pencil plus line. Okay. I did an example for pencils. Both the size of the pencil barrel and the line emanating from the tip of the pencil have the same length. So a pencil of size 4 has a rectangular 1x4 barrel, a tip which extends to the next cell after one of the ends of that rectangle, to the center of the next cell, after a triangular tip, after one of the ends of that pencil, then draws a line of length 4 from center to center of adjacent squares. Vertical or horizontal adjacency. So it was saying that, hey, I'm getting confused. Am I doing polyomino packing? I mean, kind of. I would say, yeah. Yeah. You'd say, with the restriction that the line cannot form a cycle or branch. The line can be viewed as a polyomino of size, of the same size as the pencil. Excluding. All right. Hopefully that is enough clarification to classify the puzzle. Does this feel slow? I don't know. I sort of feel like it's the only way to actually get the insights from what we're doing. Shaka shaka. I think I know what this is, but let's see. Yeah, it's been a while, but I think this puzzle is in Puzzle Ninja. Shaka shaka. It's fun looking. I like the look of this one quite a bit. All right. Place black triangles and squares. You can only, they've got to go through the center, and, they're all diagonal. You can't place black triangles and black squares. Parts of the grid that remain white always form a rectangle or a square. The numbers indicate how many black triangles are around it. Okay. Let's give this one a try. I wouldn't be surprised if this was like an unusual one. Okay, so this 0 tells us there's no black triangle around it. Like, this just looks like this. So one thing we can notice right off the bat is that this next cell cannot be empty. It's got to have something in it. We don't know what that is, but we'll just draw the diagonal lines here to indicate we know we're going to draw something. The reason we have to is that if we didn't color this in, then we have this white shape that has this little crook in it that can never be made into a rectangle, regardless of how we do that. 2. Both of these have some kind of triangle around them. You can mark that. All of these do. All of these. If this one did have a triangle in it, then it would make this sort of odd shape that had it started here and then it went down like this or across like this, sort of like a trapezoid that we'd have to incorporate into a rectangle. So I don't think it can be here. I think this one has to be like so. We know that there are going to be triangles here and here. And we know that we've got a rectangle going here. So we're not going to be able to extend our rectangle downward into a square. It kind of has to get cut off. So I think that we could deduce that there's going to be no white facing on the top. Like this is going to be filled in one way or the other. Same for this. So that means either we're going to have the triangle that comes down like so, or the triangle that comes down like so. And the reason why we can't do this triangle right here is that that would leave this, we start making a shape around this 3 that had this concave section, right? So it's actually got to be like so. No choice. And in order to make this a rectangle, we couldn't color in this triangle like so. That would create a non-90-degree angle in our rectangle. Like we've chosen sort of a side. We have to choose to make a 90-degree angle like this. Okay. And notice what that did to our rectangle over here. This can extend straight down if we want to make it bigger. Okay, we can't put a triangle on this side, so we've got to put it on this side. We can't make it come down like this because that would cause a 45-degree angle. And similarly, we can't make it come down like this. That would trap a white triangle inside. We definitely got to pick one of the two triangles that has a full side on this side. We can't pick the one that looks like this because that would cause a 45-degree triangle, so it's got to be the other one. And there are probably faster ways to reason through this, but I don't know what those are yet. We're sort of, again, we're forced to create 90-degree angles for our rectangles. We can tell this rectangle is sort of starting this way, going to kind of go down this diagonal direction. How far, we don't know. We've got to avoid making anything but a 90-degree angle, so we've got to fill in this one like this. And at some point, we're going to need a triangle that kind of cuts off this. It could be this one, or it could be this one. I'm not sure yet. Let's see, where would we go from here? We could, well, down in this square, we know that if we chose a triangle that goes like so, then we would cut off this white area into a triangle. And similarly, if we cut off the area that goes like so, we'd make a non-90-degree angle. So we can't do either of those. We have to fill in this one way or the other. And we know that we can't use this triangle because that would create a 45-degree angle. So we have to use the other one, this. Go. Again, we're forced to make our 90-degree angle. All of our white regions have to be rectangles. Okay. So this is the puzzle. I guess what's interesting about it is that we've got these local rules, but we don't know how big the rectangles can get. They could impinge on one another in some interesting ways. Yeah. I see that Nikoli uses a notation like this to signify that the rectangle is not going to get filled in. I think that's a good notation. We like put a box around it. I think there are only certain angles that will fit smoothly with this one that we've got. So for instance, the triangle that goes like so. I'll say like, I'm going to start referring to them by which corner is double filled in. So this would be southwest. Southwest doesn't work. Southeast might be okay. Northwest doesn't work. Northeast might be okay. There we go. Let's see here. Northeast doesn't work. Northwest doesn't work. So we definitely got to pick one of these two. Can't be like this. It's got to be like this. Southwest didn't work because it would create a 45-degree angle over here. What's interesting about this now, I think, is that if we dotted right here, then we'd create a trapezoid shape. So this can't be a dot. It's got to be a triangle. We can't do southwest or southeast because we'd create a non-rectangle up here. It's got to be north. If we did northwest, then that would create a trapezoid with this one down here. Really a parallelogram, I guess. So it's not going to be that one. It's got to be this one. You can see how we're kind of committed to a rectangle that's at least this wide. maybe it would come down like this. Or maybe we continue all the way down to here. We don't know yet. We can be positive that we're not going to fill in either along the diagonal, southeast or northwest, because that would interfere with either of these being a rectangle. If we did this one, then that wouldn't work. That would interfere with the rectangles. And if we did this one, that wouldn't work. So this is going to be empty. So now it's possible that our rectangle ends here. All right. I guess one way to mark this a little bit is to say, when we're eliminating rectangles, we could say, yeah, it's not this one. We know that it's not going to be this one. We know that it could be this one, or this one wouldn't work though. So our two choices left are do nothing, or fill in the triangle that has the corners of south and west. We can probably perform this analysis in the other squares too. This one's not going to work. That would create a weird angle. This one's not going to. We can be sure that this is the one, since we're sure that we have to make a mark here. That's what that little X means. Try this corner over here. Yeah. Be sure that these aren't going to work, so this edge is definitely going to be filled in. This one actually doesn't work, so this one actually is the only one that's going to work by process of elimination. If this one weren't empty, the only way to make this all rectangle would be to leave this, would be the southwest triangle. But the southwest triangle creates problems for this one. So this is going to remain empty. As this remains empty, we need to continue the rectangle over here, sort of parallel mirror image fashion. And if we did empty out this one, then we'd start getting a non-rectangular shape. So it's definitely got to be used. And really the only way to do it at this point would be to fill in this right here. There we go. Beautiful. Now you can see our rectangle that popped out of there. This would make a non-rectangular region, as with this. This. So this one is actually not filled in. We know it has to look like this. If it looked like this, if we use the northeast triangle, then we'd get a non-rectangular region over here. So it's got to be the northwest triangle. If we left this one empty now, that wouldn't work. So we've got to use the southwest triangle. Notice how we made a little rectangle here. A 1 by 1 square is a rectangle. could start making, yeah, if we stuck a triangle in here, any of them, with the possible exception, well, no, now it's true. If we did the southwest one, that would mess up with this region on the left. If we did any of the other ones, they're going to mess with the region on the right. So this is going to be empty. And so with what we've got going on so far, making symmetry arguments, we're going to need this. We're going to need, and since when we've got some mandatory spaces left next to each other, they're sort of forming half of our shape, and we have to fill in the other half of the shape. It's a little hard to explain that, but I guess the point is that if we're all rectangles are symmetrical, and so if we would be tempted to make a non-symmetry, then that can't be part of our solution. Okay, let's consider this square next. This one could be okay. This one will break our shape on the right. Well, this one, as we're leaving it empty. So we're forced to put in the northwest triangle. And to close off this rectangle, we certainly can't put in leave it empty. So this is the only thing that's going to work. All right. So we're making pretty good progress. It's tempting sometimes to leap ahead and go, hey, can I just draw something that will solve the puzzle without thinking your way through each one of the possible scenarios. So for instance, there's a scenario where we leave this blank, but then we have to fill in this triangle. There's a scenario where we leave this blank and have to fill in this triangle. And it's not obvious right away which one is which, or which one's viable and which one's not. So we've got to kind of figure that out slowly. Similar idea over here, but we can eliminate some of these triangles right away. Can't do this one, or this one, or this one, or I guess this one. So this actually has to be open. So now we can't, if this is open, then these ones have to be used. Helpful. How about this one? If we did this one, that wouldn't work. This one would be like creating some weird trapezoid thing. Trapezoid. This one might be okay. Oh, but if this one happened, then we'd have a little triangular region. So that one's not okay either. There we go. So this is going to be a region. And we actually need to cut off this region. It can't go around a corner. So we're definitely going to have either the northwest or northeast triangle. We can't use this one or this one, I guess. And we can't use the northeast because that will make a triangular region down here. So it's got to be this guy right here. Make our 45-degree angle to a 90. And we're forced, because we have 1, 2, 3 triangles around this one, we conclude that this one must be empty. Can't use either of these triangles. They'll create weird triangular regions. How about northwest? It's okay. Northeast wouldn't work. So since we are forced to fill it in, it's got to be this one. Okay. We did this bottom triangle, then we'd create a 135-degree angle. That won't work. We did this one. Then we definitely create a 45-degree angle. That won't work. We did this one. We did close the triangle. We did this one. Potentially that would work because we'd have a flat line here and a flat line here, but then we'd get this 45-degree angle again, so that wouldn't work. So this has to remain open, and these two have to be used. This one would create some weird shapes. This one might work. This one won't work. And this one won't work. So we have to go with the one that would work. Here. Okay. Doesn't work, doesn't work. I mean, there's a symmetry argument here that like we can't cut this one off without messing up this shape. It's got to stay empty. And then by symmetry, we got to do this and this. Okay, so at this point, I'd kind of go, okay, I think we've made a decision about every square. Let's go back through and check. Have I got the right number of triangles? 2, 1, 0, 3, 2, 3, yep, 3, and 2. So all that is checks out. Have we got any non-rectangular regions? No, I don't think so. So yeah, if we look at the Nikoli solution, yeah, they are identical. That was a long one. And those are interesting puzzles, right? Really different from any of the other ones that we've looked at. But yeah, it's kind of the same process of elimination, trying out possibilities, knowing that certain cells have to be filled in or not. But then this like geometric restriction, which has either diagonal or you could say, I don't know, what do you call them? Orthogonal? Orthorectal? I don't know. Either diagonal or up and down rectangles. That's interesting. I think it's unique to this puzzle. All right, let's look. Shaka shaka. Place objects with row column counts. I wouldn't say that. Region, because we're not doing rows and columns. There's adjacency. Right. How many triangles do you put adjacent? Yeah. I do think that there's this geometric tiling is a way to talk about that. Matching a shape, like tangrams, is kind of like that. Region fill with region cardinality. Yeah, there isn't a region cardinality. There's sort of an adjacency cardinality. So let's talk about that. I am more inclined to split it. The geometric shape making is seems to be different. I also wouldn't call it region cardinality. It shares more DNA with a slither link that indicates how many neighbors must satisfy a certain property. How many neighbors must satisfy a certain property. edges cells. Okay. Do they call it lanterns? I forget. It's Akari, right? Lanterns. Yeah. Right. Or Akari, or maybe even closer to Akari that specifies the number of orthogonally adjacent lanterns. Okay. What does it say about Akari? Place objects with row column counts. I wouldn't say it's like, that seems a little odd too. Tents places objects with row column counts. I don't know if tents is in the list. It has low. Cardinality. Let's see what USO1 is. All right. Interesting. Minesweeper style clues. Here, I'll show you USO1 so we can discuss that together. Minesweeper style clues, but in each region there's at least one wrong clue. And then how many colored cells are next to a cell vertically and horizontally? So it's not the number of mines in the 8 surrounding cells, but it's the 4 next 2 cells. In each rectangle bordered by bold lines, there's one wrong number. And colored cells cannot connect horizontally or vertically. And white cells form one big graph. Okay, let's try this puzzle. It's not possible for this 3 to be right because there aren't 3 places for bombs next to it. So it's the liar. And this is the truth. So it's actually 2. If we want, we could draw that in. And this one is correct. So this is a mine here. That makes this 0 wrong instantly. So it's got to be 1. And this is not a mine. Not a mine. This wasn't correct, but it's still 2. Oh, it's not correct. It doesn't mean it's 1 or above or below. It's just wrong. So it definitely can't be 3. But these ones would be correct. These 1. This one definitely can't be correct because there aren't 4 slots for to put in. It means this 1 is correct and this 3 is correct. Well, if the 3 is correct, that's very consequential. And we also have a rule that we can't have bombs next to each other. And we can't cut off white from the rest. We've seen some of these already. We don't know yet if this is a true clue or not, but we know that this 3 is correct. Actually, we could tell. This 3 is correct. This 1 is wrong. I'm using the notation I saw on their website for this. So this one doesn't have necessarily be 1. Maybe that's a bad inference, I think. It's just wrong. This one is right, though. So that would be like so, and this. If it's wrong, it just doesn't tell you anything. It tells you that it's not 0. That's all it can tell you. Just like this one is not 4. This one would definitely be correct at 1. This one or this one. Can't be next to. It's got to be this one. Again, can't be next to. Can't be next to. Can't be next to. Can't be next to. And I think that's everything. We've crossed out at least one liar per region, and we've made a decision about every square. So let's see if our solution matches Nikoli. It does. On row 2, we've got 1 and 4, we've got 3 and 5, 1 and 4. 1 and 4, 3 and 5, 1 and 4. Yep. So that's it. That's USA 1. Okay. Region cardinality. Yeah, I wouldn't call it region cardinality either. Not have region cardinality. However, it does have a region property. Exactly 1 incorrect clue per region. I think local cardinality is a better way to talk about clues. And we also have no adjacent shading. Okay. We went over the 3 new entries. We went over some class fit caveats. Juo-san. Did we finish looking through the merge notes? All right, let's look at Juo-san. Fill all cells with a vertical or horizontal line. And again, I hope you know that we're not memorizing solutions. Not that interesting. Areas enclosed by bold lines or territories. The number show how many more of the vertical or horizontal marks they get. There are also cases where the number are the same. Territories with no numbers can have any number of vertical and horizontal marks. Horizontal marks can extend across more than 3 cells horizontally, but not more than 2 cells vertically. Vertical lines can extend across more than 3 cells vertically, but not more than 2 cells horizontally. So I guess this is sort of an idea that we're not putting too many vertical lines next to each other or too many horizontal lines next to each other. Solution. Let's look at Joseon. All right. Okay. So I think the kind of inference that we're intended to make is how many more of each one they get. Okay, so it's this number 3 right here is the difference between the number of horizontal and vertical lines that we can get into our thing. And so, for instance, starting with this 3, you can say there are 3 more horizontals than verticals, or there's 3 more verticals than horizontals. So that means in this region it's actually all or nothing. And then we also read that we can extend horizontal marks across more than 3 cells horizontally, but not more than 2 cells vertically. I think that should say more than 2, but anyway. So horizontal marks and verticals can extend across more than 3 cells vertically, but not more than 2 cells horizontally. So look at what happens if we make a vertical mark here, here, and here. We would have vertical marks that extended across more than 3 cells vertically, or 2 cells horizontally. So that doesn't work. We actually have to pick horizontal for all 3 of these. Does that kind of make sense? So because the difference would have caused us to put 3 vertical lines in a row, that doesn't work. Okay, so down to the next one. Here's for a very similar reason, we've got to put 3 vertical lines here, because otherwise we'd have to put 3 horizontal lines. Similarly for this one. Okay. The numbers in the territories show how many more of the vertical marks they get. It seems weird to me to put a difference of 1 into something that has 2 cells. I guess it means they can't both be the same. I would think that this should be 0 or blank. Right? Because the difference should either be they're both the same, 0 difference, or 2 difference, I guess, or they're both different, which means 0 difference. 1 of each. So I'm a little confused by this 1 right here. I don't think it's about difference, if I had to say it. Huh. Let's revisit that. I'm not sure exactly what it means yet. If I interpret their solution a little bit, I'm sort of cheating by looking ahead. It seems like which one has the most when you compare vertical and horizontal lines, what's the number of the one that has the most? So this one, it says there's 3. This one has 3 of the whichever one is in the lead, and this one has 3 of whichever one's in the lead. This one has 3 of whichever one's in the lead. And then this number, it says it has 3 of whichever one's in the lead, and there's another 1 of the other one. This one says it has 4 of whichever one's in the lead. So they all have to be the same again. That kind of implies that we need to do like this. This one says it has 4 of whichever one's in the lead. So it has 4 of one and 2 of another. This one would be 1 and 1. And then, yeah, this one is going to be 3 and 1. I think that's the way to interpret these rules. At least what I'm seeing in the solution. Okay, well, let's try and continue. From here, we'd have 2 horizontal lines and a vertical. We can't make a third one, so we've got to put a vertical line here. We can't make a third one of these vertical lines next to each other. We've got to do a horizontal on this side and on this side. We can't make 3 vertical or horizontal lines in a column, so we've got to put this way and this way. I'm pretty sure that we're interpreting this rule right now. We can't make 3 vertical lines next to each other. We've got to go this way. Now look, we've got 2 and 2 of each in this region that has 4. We're going to have 2 of one and 0 of another one. If they were both horizontal lines, then we'd violate the rule about having a bunch of horizontal lines in a row. So we'll make them vertical. This one, we have already a vertical line, but we have maximum 1 of each. So it's got to look like so. We can't have 3 horizontal lines in a row. This is going to be vertical. And now we have to pick between having 3 verticals and 1 horizontal, or 3 horizontals and 1 vertical. If it's 3 horizontals and 1 vertical, we'll have 3 horizontal lines in a row. So these are both vertical. All right. On that interpretation, let's see if we did the puzzle right. 3 horizontal, vertical, horizontal. Check. Vertical, vertical, and then all horizontal. Check. Horizontal, vertical, vertical, horizontal. Yep, check. Vertical, vertical, horizontal, vertical, vertical. Check. Vertical and then 4 horizontal. Check. Okay, so let's use that as our interpretation. I played a sample puzzle for Juoson. Let's see what the particular complaint was again. How many more? Okay. I believe the correct interpretation is as follows. Number in each region corresponds to the number of the count corresponds to the higher count. Whether it is the count of vertical lines in the region or horizontal lines in the region. This puzzle can probably also be interpreted as filling in ones and zeros. If we assign 1 or 0, if we assign them to the rules about not having 3 of the same, if we assign them arbitrarily to the rules, e.g., no 3 zeros in a vertical row, no 3 ones in a horizontal row. In a vertical slice. Yeah. It does make a kind of cute picture, but I don't think that there's anything different about making them, you know, horizontal and vertical lines versus zeros and ones. Okay. Have we resolved pencils and Juosan? Yeah, I think we did. So that's everything. Let me know if any more input is needed. All right. Well, we've been doing a lot of puzzling as we've been going through here. I hope that's been entertaining for you, as well as it is for me. And hey, I just saw a follow. Thanks for the follow. Sorry, I usually have that stuff up, but we're going back and forth between browsers a lot today so that I can pull in some of these puzzles for your knowledge and entertainment as we decide if we're really speaking the same language with the robot about the mathematics behind all of these puzzles. I don't know about you, but this feels like yeah, a good 2 hour session. I guess again we're kind of in the driver's seat still. We're using our human judgment on these things. We're trying to understand these puzzles in a deep way. It does seem to be I didn't really expect this, but it does seem to be trying to understand the decisions that I'm making and storing them for future reference. Uh, I don't know if I expected that or not. I guess it's nice. It seems like the kind of thing that you would want as you're building institutional memory. Now, I wonder if this memory bead is the format that we're going to want to use for our knowledge discovery. Um, it's pretty hard for us to export that format as opposed to like, go read this document if you want to know how Dan thinks through puzzle problems, local cardinality clues. Okay, let's see how it's going. It's kind of weird to have to keep going in and out of scrolling just to see what's going on. But that's just the technology that we're using right now. That's sort of what Gas City is affording us. So added more to the schema. This is reflecting our stuff. Um, it's I think it's really fun to me that we're getting these sort of they're not exactly children's games per se, but simple recreational entertainment, and then we start very quickly running into you know mathematics, lots of mathematics. I think I have this intuition that a lot of games that we play are sort of thin covers over mathematics, or that if games are logical, if you can follow them using their rules and don't get stuck in blind spots or corners or something like that, then there will be a mathematical formalism underneath them. It's like those are the two sides of the same coin, right? Like a logical structure dictates that as we're playing this game, we're not going to get stuck. All right, so it's making some updates reflecting our feedback. I think I'm gonna call it there for now. Probably go get some lunch. Oh, I guess we're gonna see. Yeah, it's still working hard. So we're gonna pick it up from there. Maybe I'll get some more time to go through this later today. Well, as always, thank you for watching, and I hope you had some fun. See you soon.